but it's really difficult to see the board on the video. So it's kind of difficult to follow what you're saying.
Oh, really? That is true for the video lecture 1. For lecture 1, our assistant did not realize the best way to taping the lecture. And we found that, as you said, it's not easy to see what I wrote on the whiteboard. So actually they are now zooming the whiteboard. So you can see what I wrote on the whiteboard from lecture number 2. So you didn't try to see the lecture number 2?
No, not all afterwards.
Okay. Right. And if you have some comment, just leave your comment on our homepage so that we can improve it. Other comments on videotaping? No? Okay. Let's move on to chapter 2. Response to harmonic excitation. What does it mean by harmonic excitation? What is harmonic excitation? Sine function. Harmonic excitation is some excitation has a sine form or cosine form. Okay? Is it harmonic? What's the difference between harmonic excitation and periodic excitation? Have you ever heard about periodic excitation? No? This is a harmonic excitation because the frequency is 1 kilohertz and up and down. 800 hertz? That's what you heard? This is 1 kilohertz. Yeah. Very good. Periodic excitation is because it has a period. Is it harmonic excitation? Yes. Because this can be expressed by superposition of sine and cosine. Therefore, he argued that this is harmonic excitation. Then what about this kind of excitation? This kind of excitation. Is it harmonic? Periodic? Famous Fourier said, any time function xt can be expressed by the superposition of a harmonic function. Because that's what Fourier said a long time ago. Cauchy really condemned saying that, hey, you know nothing about the mathematics. How can you say non-periodic function can be expressed by the superposition of periodic function? That's nonsense because that's logically not correct. But in fact, non-periodic function can be regarded as one segment of a periodic function. Therefore, everything is periodic in general sense. Therefore, every function can be expressed by the superposition of harmonic function. Therefore, every function can be expressed by sine and cosine. Therefore, we are learning harmonic excitation. Right? We are not studying very special case. Very special meaning that very special which is not likely happen in real world. But what happen in real world can be regarded as superposition of harmonic function. Therefore, if we do know very well about what's going to happen due to the harmonic excitation, and this is the linear vibratory system, and using principle of superposition, we can understand the response due to general excitation. Okay? That's the reason why we are learning response due to harmonic excitation. Let's start with simplest case, right? What is it? Single degree of freedom. And a harmonic excitation that has some magnitude and cosine omega t. I don't know why Professor Inman used cosine omega t instead of using sine omega t. It really doesn't matter. Right? When you read the book and you might have a question, why he used a cosine omega t? I don't like a cosine omega t, and because in chapter 1 he always uses sine omega t. Right? But it really doesn't matter because cosine omega t and sine omega t is only phase difference pi over 2. And this is magnitude. Magnitude of excitation. Or magnitude of input, magnitude of a forcing function, and this omega is not same as omega n. Omega n is natural frequency, that's the characteristics of vibratory system. And this we call input frequency or excitation frequency or forcing frequency. Okay? Meaning that I am exciting this system that has natural frequency of what is the natural frequency of this? Is it 1? Really? Oh, this is about 1. Yeah? Okay? And the excitation frequency can be very small compared with 1 or larger than frequency 1 or very similar with frequency 1. Okay? Depending on omega forcing frequency, the response